All right. Yeah, hi everyone. So my name is Daniel Muthakrishna and I'm a postdoc at MIT. I'll talk briefly today about what I think is a pretty important issue in upcoming transient surveys, which is how do we prioritize follow-up when we have such large volumes of data. So we're at this pretty incredible time in astronomy where we have more data available to us now than ever before. And upcoming surveys, such as the Rubin Observatory shown in the background here, are kind of going to transform our understanding of the transient universe, right? They're going to observe millions of alerts every single night, an order of magnitude more than any survey to date. And so I think as such, new and novel methods, such as machine learning, are really going to be necessary to be able to process and classify the amount of data coming in. And so one little animation I like showing that kind of sets the scene a little bit is this is every single supernova we've ever seen since the year 1054, when Chinese astronomers first looked up and saw a new star appear in the sky, up until about 2018, right? And it might sound like a lot, right? We've got 13,000 events plotted against the night sky, but it pales in comparison to what LSST is going to do, right? The Rubin Observatory is going to observe over 10 million transient alerts every night, right? An order of magnitude more than any survey we've seen before. And the issue is that transient surveys have largely been driven by human eyes, right? It's taken human eyes to decide whether something's interesting, worthy of follow-up. And the other thing that's interesting and problematic is that the more that we've looked at the transient universe, the more that we've realized how mysterious and unusual it really is, right? So here I plot most or some of the known objects in the transient universe, where I plot peak luminosity against characteristic timescale. And in the gray regions, we have these things we kind of understand, like type 1a supernova and type 2 and 1bc supernovae. And in the colored regions, we have these rarer phenomena, things that maybe we don't understand as well or are relatively recently understood. Things like kilonova, where we only have one observation of, or tidal disruption events, superluminous supernovae, and calcium-rich gap transients, right? And we know that new surveys are going to observe unprecedented numbers of these types of objects. But as well as that, we know that we're going to explore entirely new domains, right? LSST is going to look deeper than ever before, and so we should expect the unexpected, right? And the issue is that discovery has been driven by serendipity so often in astronomy. So often it's taken a trained astronomer to look at an object and say, hey, that looks funny, or that looks interesting. Let me point my spectroscopic telescope at it and get further measurements, right? From FRBs to pulsars, et cetera, right? We've done this so often in astronomy. But when we have such large volumes, it's unclear about how we get lucky, right? How do we find the needles in the haystack? How do we find what's interesting? How do we classify what's not, or what's interesting and what's not, right? So I think automated anomaly detection algorithms are going to be necessary as well. So I think what for prioritizing follow-up, three criteria I think are quite important for transients. Classification, which is identifying what we think is interesting and what we should follow up. And then automated anomaly detection, which is things that our classifier or supervised learning algorithms can't identify. We need a way of identifying or picking them out automatically, right? And in the case of time domain science, or transients in particular, identifying how early we think we've found it is also just as interesting, right? We want to find things ideally before maximum or as early as possible after the explosion, so that we can try to understand some of the progenitor physics. And I think all of these things should be done in real time so that we can update our probabilities as we get more observations coming in, right? And so one of the reasons I think early identification is important is, for example, in the case of type 1a supernova, right? We use type 1a supernovae to understand cosmology and to show the universe's expansion rate was accelerating, but we don't actually understand the progenitor systems that well, right? Despite how widespread their usage is, right? We don't know if it's a single degenerate white dwarf system where you've got a carbon-oxygen white dwarf orbiting a massive star and accreting mass until it reaches the Chandrasekhar and explodes, or if it's a double degenerate system, right? We don't know which of these populations or which of these dominate the population of type 1As, okay? And we also don't know the explosion mechanism. And the only way to break this degeneracy is to get early time measurements, right? Observations in the early part of the light curve just after an explosion will have a flux excess caused by the explosion hitting the companion star, and we should see some sort of flux excess. If we measure that flux excess, we can get some idea of what the progenitor system is. In fact, we have a paper out this few weeks ago on tests where we put some upper limits on this. But the main idea here is that getting early time measurements are important, and it's the only way to break this degeneracy. Okay, and not just for this, but understanding progenitors in general for all sorts of different transients. Okay, so what have we done? So the first thing we've done is classification. And so one tool I built is called Rapid, which does real-time automated photometric identification. And since this came out, there's actually been a whole heap of other different classifiers that are doing similarly well on, or even better on the data sets, right? So here, the idea is that as we get observations, we've got in the G and R passbands, in the ZTF, for example, we can update our probability. So for example, here you can see in this light curve, at the start of this curve, we predict it as pre-explosion, this gray line, and as the light curve evolves, this green line becomes more and more confident, and by the end of the light curve, the model is pretty confident this is in fact a type 1a supernova, right? And so that's the kind of model we want to build, where we can update our probabilities as more and more observations get in. And the way we built this was with a recurrent neural network, right? So we use something called a gated recurrent unit, which helps with long-term dependencies. And the idea is that we pass in our flux information as a function of time. So at every column here is a different time step of information, where the input is on the top, showing the top panel effectively, which is maybe our passband and its fluxes at every time step, and any other contextual information we might want to pass in as well. Okay, we pass that into two gated recurrent units, layers gated recurrent units, where the idea is we get two inputs, not just the current time step input, but the previous network representation as well. Okay, and then on the output, we're predicting the class probabilities, and that's what we're plotting on the bottom here. So we have a vector of probabilities, identifying what type of class is the most confident. And we train that up, train on the training set, and we get something reasonably well on that object here. And we can then get metrics as a function of time as well, right? So here you can see our performance on the entire test set, and you can see that our performance improves as a function of time, right? As we get more observations, we get better and better confusion matrix, right? And similarly, our ROC curve improves as well. All right, so it's not too bad. I've got some undergrads at MIT who are doing some fantastic work on improving this, and it works reasonably well on the simulated data. But getting this to work on real data is a real challenge. And if we go straight from that rapid that's trained on simulations to apply it to real data, we don't do so well, right? So here, we don't have that many real classes. We've only got 4 classes that we can actually get a reasonably sized training set from, whereas we have a lot of prediction classes. And so here you might be able to say we can combine the type 1a supernova classes and say that we get an effective accuracy on type 1a supernova around 75% if we combine those first 2 blocks. But the others aren't so good, right? So training on simulations and applying to real data is problematic. And so we really do need to train on real data as much as possible. And I have a student working on this where he's done some data augmentation using a Gaussian process, and has been able to perform reasonably well on a test set of ZTF data, a real data set. And so this is in work in progress. And I think we'll get there. And I think classification, there's a lot of teams working there in the community that are trying to get ready for LSST when it starts in 2025. When we have these huge surveys coming online. And I think we will get there. I think classification is something that will be reasonably okay by the time 2025 hits. But one issue I think we're not ready for is anomaly detection, right? So things that classifiers can't deal with is something that's a lot harder to find. Like, how do we find things that we don't know to expect or that we don't have a good training sample of, right? So I think the classical ways that anomaly detection is looked at and we consider, so this is the second part of this talk, I guess, is we typically do some sort of clustering and then look for outliers, right? So we cluster our data in some sort of parameter space and look for things that are further away. Things that are further away have a larger distance away from a cluster. We identify them with higher anomaly scores, right? So that's a classical approach. Another commonly used algorithm, something called an isolation forest, where basically you just do an ensemble of decision trees. And the general principle is that things that are easier to isolate, things that separate more quickly along a decision tree, are more likely to be anomalous because they had features that separated them quickly, and things that are harder to separate are more likely to be inliers or common types of events, right? And so using that, we can come up with some sort of metric for anomaly score. And so these are the two perhaps most commonly used techniques for anomaly detection. And the general idea, I think, for anomaly detection, you do these two things, right? First, you want to do some sort of dimensionality reduction or representation learning, where you condense your input data into some sort of parameter space, okay? And typical ways to do that, at least in the transient domain, is you do some sort of feature extraction, where you take your light curve and maybe you extract moments of the data, statistical moments, or other information you think is important. Or you do this in an unsupervised way, where you do some sort of autoencoder, for example, and you compress your space into some latent space, and then do anomaly detection or some sort of outlier detection algorithm on that latent space, right? And so that's a typical approaches. The issues here is that these often aren't very good representations of the data. And we talked about this a lot yesterday at the debate, but often the latent space here might not be able to characterize the things that we're looking for well, which is how do we separate these classes, right? And so can we separate classes? Can we separate outliers from inliers? Is there any guarantee that this latent space will separate things that it's never seen before versus things that it has seen? Okay, and there's not such, right? And so one simple idea we've done, is, which does help to actually just generate a latent space, is just take that classifier we developed earlier, right? And then just extract that final layer, right? Take that final layer that has already been trained on separating classes pretty well, right? And if we take that out, we take this dense layer and plot that into, look at that latent space here. I've plotted a UMAP representation of it in 2 dimensions. You can see that it somewhat separates classes, at least the training classes it's seen before. And so only training on these classes, we separate the classes like such, and then testing it on an unseen data set, we can see that it actually does separate classes it's never seen before somewhat reasonably as well. And so these are what I identify as the rare classes or the anomalous classes in my data set. Okay. And so the general principle is I then take this latent space, I train an isolation forest. So I pass this into an isolation forest, I train it to be able to separate each of these classes and find things that are not like it, okay? And I get some sort of metric of anomaly scores, right? And so this works reasonably well, where things that are common, so the top half of this list basically, have low anomaly scores, and things that are rare have much higher anomaly scores. So we get that first order separation. And so that works reasonably well. And it's the first order success, I guess, of anomaly detection that we can do for transients. And we heard from Maria in the first day about other approaches using isolation forests as well. Okay, so I'm not going to talk about this for the sake of time, but doing this in real time is quite interesting as well. And the third thing I want to talk about, just finally, using a very similar method, is can we predict the transient age and predicting this in real time? I think a third criteria that's important to prioritize follow-up. And so we've got some students here, and the general idea is, can I predict the epoch of the transient I'm seeing? So if I look at a light curve, can I identify the time of maximum, the time of explosion in real time? And so here we built a recurrent neural network again, same kind of architecture, where I pass in my inputs, just time, wavelength, flux, and uncertainty. And my output, instead of being the class, I've just changed my output and I'm training it on the specific age of the transient, right? And so this would be the time since maximum or the time since explosion. And I do this in a probabilistic way. I model that output as a normal distribution. And so here I can plot my predictions and I get uncertainties on those predictions of the time of maximum and time of explosion as well. And so we do reasonably well on the test set. And you can see that as a function of time, our predictions improve. And as we get more data, our idea of when explosion happened or when maximum happened improves. Okay, so let me just wrap up there and say that we've tried 3 different methods, which I think are important, 3 different criteria for preparing for the new era of transient astronomy: classification, anomaly detection, and predicting transient phase. And all of these need to be done in real time and be done as quickly as possible. And so neural networks can really help us there. Thank you.
All right, thanks, Daniel. Do we have any questions here in New York first?
Yeah. Like early detection for the anomaly detection. Do you have, like, as part of your training, like, oh, if we have like an incomplete light curve, basically, or I guess how do you model like an event in progress?
Yeah. So for that particular algorithm, I have another algorithm for real time. For that particular algorithm, we just pass in partial light curves. And so although we've trained on a large data set, some of that data set only has partial data because weather reasons, et cetera, and some of it doesn't. And so when we do try this and actually try it on the full on a full data set and just look at how we perform as a function of time, where we just chop it off, it does reasonably well, and we can still get reasonable scores as a function of time, and even if we just chop off the end of the light curve.
Yeah. Anything on Slack? No? Do we have a question from Paris?
No, I don't see question in Paris.
Okay, well, let's thank Daniel
I
one
got
more
one,
time.
sorry. I got a question here.
Oh, okay.
Yes,
Too soon.
yes, sorry. I was wondering whether you deal with the constellations of satellite. I mean, I saw some blue item in the first slide or the second slide where you have robotic exploration, and I was wondering what it is, whether you have to handle these issues in the classifications like satellites, etc., etc., or whether it is really in the time domain that you see things.
Yeah, no. So when you say satellites, I assume you mean like literal satellites, artificial satellites, or
Yeah. I mean, yeah.
oh yeah, okay. Yeah, so no, we don't deal with that. We don't deal with asteroids at all. I do think that maybe they would pop up in the data set because they will look a little bit funky. But the hope is that these things can be cut out before it even reaches these algorithms. If we do put this into practice, I think we'd really need to separate and have other algorithms that are dedicated to finding these events and moving objects like such. But we haven't tried to deal with those things at all. I think that they might look interesting and they might pop up as anomalies, but I'm not sure.
Okay, great. So now let's thank Dan one more time.